A large reason of why we learned about exponential and logarithmic properties is because it allows us to solve exponential and logarithmic equations. As always, feel free to use the timestamps in this video to jump to a particular topic of choice if there's something specific you want to know about. So for exponential equations, the nicest exponential equations are whenever we have the same base of something is equal to the same base of something else. Because since exponential functions are one-to-one, that means that their exponents have to be equal. And we've actually used this logic a lot without necessarily naming it, because if, for example, 4 to the x power is equal to 4 squared, then you know x has to be equal to 2. And the absolute nicest way that this type of problem can be given to you is if those bases already are written to match. So we'll go over in a moment how we can make those bases match if they don't. But if they already match, just use the fact that you know this logic. So if 2 to the x minus 1 is equal to 2 to the 2x minus 4, then we know x minus 1 better be equal to 2x minus 4. And then we have a nice linear equation that we just solve for x. I personally like dealing with positive x's, so I'm going to undo x on the left by subtracting x on both sides. X minus x makes 0. I'm left with negative 1 is equal to 2 minus 1x leaves me with x. Drop down the negative 4. And then as a last step, I want to undo subtracting 4 by adding 4 to both sides. Negative 1 plus 4 gives me 3. And then x is equal to 3. It might be worth double checking by plugging in. 3 minus 1 gets us 2. 2 times 3 minus 4 also gets us 2. And you're good. And you don't have to worry about domain either, because for exponents, I'm allowed to plug anything into an exponent. Go ahead and try this next one yourself and then compare with what we get. This is set up very similarly, where we have same base, and we just have two different things in the exponent. So we know that logically, x must be equal to 3x plus 2. Then we want to go ahead and solve for x. So we first want to subtract 3x from both sides. I'm just doing that since I noticed the left-hand side already only has x's in it. 3x minus 3x makes 0. X minus 3x makes negative 2x equals 2. And then as a last step, you're going to divide by negative 1 on both sides. So x is equal to negative 2 as your final answer. Now, oftentimes you're required to do just a little bit more thinking than that, and that you are known to have the knowledge of how do I rewrite numbers so that they have the same base, if it is possible. It's not always possible, but if it is possible, it's going to be much nicer than some of the other methods we're going to go over later. So here, they're not pre-given to us in the same base, but I can rewrite them that way. In particular, 16, I hopefully recognize is the same thing as 4 squared. So I can go ahead and set up that this is really 4 to the 3x plus 1 is equal to 4 squared. And now I'm good to go ahead and make my equation, because now that they have the same base, that means 3x plus 1 better be equal to 2. I want to continue to solve for x, so I'm going to undo any addition subtraction first by subtracting 1 on both sides. 1 minus 1 makes 0. 3x is equal to 1. And then as a last step, I'm going to undo multiplying by 3 by dividing by 3 on both sides. So x is equal to 1/3. For this next problem, we can indeed still rewrite these as the same base. And if that base is not initially sticking out to you, you can do some educated guessing and checking on a calculator as well. In particular, I noticed that both of these are even. I might want to even just check naively if 32 to some power gives me 256, it's way too big. Hopefully you had some intuition that might be way too big, but even if you didn't, you can go ahead and check that. Then I want to think 32 is the same as something to what power? Maybe I might be hopefully thinking 4, but if I start checking that, 4 squared is 16 times another 4 is 64. 4 is going to be too big. Since they're both even, how about let's check 2? So in this case, 2 to the 5th power is 32. And now I might want to check if some bigger powers will give me 2 to 256. So 2 to the 6th power gives me 64. 7, we're not quite there, but 8, I'm in business, that's 256. So you may have to do a little bit of educated guessing and checking if it's not coming out right away. Typically on an exam, you won't be required to recognize anything much larger than something to the 8th power or so, but it's always good to keep in the back of your mind. So here in particular, Now that we know that, we can rewrite 32 as 2 to the 5th power, all being raised to the negative x plus 26. If you'll notice, I added in parentheses there just so that I'd make sure I don't mess up that part. And then the 256 is the same thing as 2 to the 8th, all being taken to the x. Then I want to utilize my exponent properties to know if I have a power of a power. That's the same thing as multiplication. So that becomes 2 to the 5 times negative x plus 26 is equal to 2 to the 8x. I may want to go ahead and distribute that 5 as well. 5 times negative x is negative 5x. 5 times 26 is something that I should probably know off the top of my head, but even if I don't, I can just do a little bit of math off to the side. 6 times 5 gives me 30. 2 times 5 gives me 10 plus 3 makes 130. So this is 2 to the negative 5x plus 130 is equal to 2 to the 8x. And now that I've totally simplified within each of these exponents and they have the same base, I'm good to go to actually set up my equation. So that becomes negative 5x plus 130 is equal to 8x. Now I want to go about solving for x. There's more than one way to go about it, but I might notice that the right-hand side already only has x's and no constants. So I'm going to move my x's from the left to the right. I want to undo adding negative 5x by adding positive 5x to both sides. Negative 5x plus 5x makes 0. I'm left with 130 is equal to 13x. Then I want to undo multiplying by 13 by dividing by 13 on both sides. So then x is equal to 10 as my final answer. For these next problems, go ahead and pause your video and see if you can at least rewrite everybody in terms of the same exponent first. So to rewrite these in terms of the same exponent, hopefully I recognize that 16 is a power of 4. So I can rewrite this first one as 4x squared minus 11 is equal to 4 squared. We'll come back to solving him in just a minute. Let's just practice rewriting these. For this next one, 125 is indeed a power of 5. That is 5 to the 3rd power. And anytime you're kind of checking if something's going to work, if it ends in a 5 or a 0, you might want to check if it's a power of 5. Actually, if it ends in a 5 more. If it ends in a 0, you might want to check if it's a power of 10 as well, especially if it's just 1 followed by a bunch of zeros. It's going to be some sort of power of 10. So then we have 5 to the 3rd is equal to 5 to the x squared minus 2x. Now both of these are ready to actually solve. And don't freak out just because it has a quadratic up there. We've gone over how to solve quadratic equations. So for this first one, we have 4 to the x squared minus 11 is equal to 4 squared. So then logically speaking, x squared minus 11 better equal 2. Now there's more than one way to go about solving this, but in particular if you have an x squared without any plain x's, the nicest way to solve that is usually the square root property, and that requires getting the x squared by itself. So I will add 11 to both sides. Negative 11 plus 11 makes 0. I'm left with x squared is equal to 13. And as my final step, I'm going to undo a square with a square root, and whenever I do that, I need to remember the plus or minus square root. So x could be the positive square root of 13, or the negative square root of 13, which if I think about when I plug it in, negative square root of 13 squared gives me a positive 13 as well as positive square root of 13 squared, so I am good. For this next one, you want to set up a similar sort of thing. So here we have that 3 must equal x squared minus 2x. Because I also have a plain old x term in addition to my x squared term, I don't want to try to use the square root property, otherwise it'd be square rooting something that still has an x in it, not super useful. So instead, I want to set this guy equal to 0 and check, is he able to factor? If he's not able to factor, I can always use the quadratic formula. In order to set this equal to 0, I'm going to get rid of this 3 by subtracting 3 on both sides, which is really just rearranging because these are all different types of terms. So then I have 0 is equal to x squared minus 2x minus 3. Then I want to check, is this guy factorable? So I want to ask myself, is there anything that multiplies to negative 3 but adds to negative 2? I am in business because that would be negative 3 and positive 1. And since the coefficient is in front of the x squared is 1, I can actually jump straight to my parentheses. Were it something else, I would have to formally factor by grouping. So in parentheses, I have x minus 3 and x plus 1. Then I want to utilize the zero product property because if I have something times something is 0, then at least one of those two somethings better be 0. So I can set up my two mini equations that either x minus 3 is equal to 0 or x plus 1 is equal to 0. Add 3 to both sides, we get that x is equal to 3. subtract 1 from both sides, I get x is equal to -1, and both of those are my solutions. It is possible we may have to combine multiple properties at once. And here, if we're going to solve this way, since 7 is prime, I'm going to really hope that all of these can be rewritten as powers of 7. So let's go ahead and double check that. So I would double check what power of 7 is 2,401. So let's check. So it's definitely going to be bigger than 7 squared, which is 49. 7 to the third gets us 343. 7 to the fourth power gets us 2,401. So we can go ahead and rewrite these all in terms of powers of 7. 49 is the same thing as 7 squared, all being taken to the x power. The next term is already in terms of 7, so I'll keep him as is, equals, and that's 7 to the fourth, all being taken to the second power. Now I want to utilize my rules of exponents, and I just want to do one at a time. So here, when I know powers of powers, I know that becomes multiplication. So that's 7 to the 2x times 7 to the x squared is equal to 7 to the 8th. Then multiplying outside an exponent becomes adding inside the exponent. So I can rewrite this first term as 7 to the x squared plus 2x is equal to 7 to the 8th. And now I'm in business because I have just base to an exponent equals same base to another exponent. So now I'm allowed to set those two exponents equal to each other. So that becomes x squared plus 2x is equal to 8. Since we have an x in addition to the x squared term, I can't really use the square root property, but I can rearrange him to be set equal to 0 and then check if I can either factor or use quadratic formula. So in particular, I'm going to subtract 8 from both sides. These are all unlike terms, so I'm just rearranging them. X squared plus 2x minus 8 is equal to 0. Then I want to ask myself what's going to multiply to -8 but add to +2. That would be +4 and -2. Now I can utilize the square root property, not square root property, zero product property, where something times something is 0 means one of those two somethings better be 0, in order to find x. So I'm going to set my two mini equations. I either have x plus 4 is equal to 0 or x minus 2 is equal to 0. So that means either that x is equal to -4 or x is equal to +2 as my final two answers. Now, sometimes you can't rewrite exponents in the same base, and that's okay. So you can instead be utilizing logs in order to solve exponents. And we can utilize the fact that we know that logs effectively undo exponents. And we're going to be using the power rule all the time when we use this method. So let's take a look at an example of this. Let's say you have something like 2 to the x equals 7. No matter how much I want to, there's no way I can rewrite 7 as a nice power of 2. But instead, I could log both sides in order to solve for x still. And you can technically pick whatever base log you want whenever you do this process. Well, I'll kind of show you both ways. I'll show you one way with log base 2 and another way with natural log. If I pick log base 2, then I'm going to say for 2 to the x is equal to 7. I'm allowed, because both sides involve terms that are bigger than 0, I can just log base 2 both sides. So what I just found out is if I have log base 2 of 2x, well, that means the x moves out front. I'm left with x times log base 2 of 2 is equal to log base 2 of 7. And what is log base 2 of 2? That's just 1. So I have that x is equal to log base 2 of 7. And that's technically a correct answer. If you're not asked for a decimal approximation, this is a number. It's the number that is whatever power 2 has to be raised to give me 7. If you're going to use natural logs instead, which sometimes on your homework you'll be asked to specifically use natural logs, sometimes you can pick your base, we can do a similar process. So if we're going to use natural logs, we start off with 2 to the x is equal to 7. Then I could instead natural log both sides. And in this case, I can still move my x out front because he's inside the exponent. So we have x times the natural log of 2 is equal to the natural log of 7. Now this time the natural log of 2 doesn't become 1, it's just some other number, But if I have x times a number equals another number, how would I get x by itself? I would undo multiplying by the number, even if he's really funky, by dividing by that number. So I can divide by the natural log of 2 on both sides. So then I get x is the natural log of 7 over the natural log of 2, which if you notice is actually the same result you would have gotten by using the original result and then employing the change of base formula as well. But both of these would be correct answers, and then if you were required to get a decimal approximation, that's when you would break out a calculator. You would find log base 2 of 7 if you're doing the first one. That would get you about 2.8. Or you could do the natural log of 7 divided by the natural log of 2. Also gets you about 2.8. So you know you did things right. So it's about 2.8. And then you want to include however many decimals they ask for. Let's look at a similar example. And here we're going to kind of show both ways. So one way when we use only natural logs. Actually, let's do that way first. We're going to do one way where we just use natural logs, another one when we pick a base. We should get the same answer both times, just written a little bit differently. So if we're going to just use natural logs, we have 3 to the 1 minus 9x equals 7 to the x. We already kind of checked with ourselves, can we rewrite in the same base? We cannot. There's nothing that I can't rewrite 7 in terms of 3, for example. So then I can go ahead and natural log both sides. I'm allowed to natural log both sides because both sides are positive numbers. If either of these was not a positive number, I would be out of luck and I just could not solve the problem. But you won't be getting a problem like that. Both of these are positive, so I'm allowed to plug them inside a log. Then we want to use the power rule. I shouldn't say you're out of luck. There are other methods you could do. You'd be out of luck for this class. Anyway, use the power rule. Move these out front. We have 1 minus 9x times the natural log of 3 is equal to x times the natural log of 7. Once you get here, your goal is to move all x's to one side, all constants to the other. And we can't quite make much progress towards that goal until we deal with the fact that we have a natural log being multiplied by something here in parentheses, and inside that parentheses is an x. So I'm going to go ahead and distribute that natural log of 3 to both of those terms. 1 times the natural log of 3 gets me the natural log of 3, minus 9x times the natural log of 3 is really just that. You can multiply it in any order, but it's really, that's all it is, equals x times the natural log of 7. Now your goal is to move anything with an x to the same side. So on the left-hand side, I notice I have a term without an x and a term with an x. And on the right-hand side, I just have a term with an x. So I'm going to move this term with an x on the left to the right. So I'm going to add 9x times the natural log of 3, whatever that is, to the other side. That cancels out to make 0. I'm left with natural log of 3 is equal to x times the natural log of 7 plus 9x times the natural log of 3. And my goal is to get x by itself. So since I notice on the right-hand side I have two terms with an x in it, I'm allowed to factor out an x, which is what I'm going to do next. So if I factor out an x, from this first term, if I do x times the natural log of 7 divided by x, I'm left with the natural log of 7. For the next term, if I have 9 times x times the natural log of 3 divided by x, I'm left with 9 times the natural log of 3. Keep in mind, these are just numbers. They're kind of funky numbers, but they are just numbers. And now I have x times something gross equals some funky number. So what will be my last step to get x by itself? How do I undo multiplying by something gross? I divide by that same gross thing. So I divide by the natural log of 7 plus 9 times the natural log of 3 on both sides. And that would actually be my final answer. So the natural log of 3 all over the natural log of 7 plus 9 times the natural log of 3 is equal to x. And then you would plug that into a calculator very carefully to get your final answer. Now, if you're not commanded to use natural log, be nice to yourself and pick one of these as the log base that you're going to use. And let's see how that actually makes your life a lot easier. So here in particular, I know that 3 has the messiest exponent. So I'm going to go ahead and say, instead of automatically picking natural log, what if I did the natural log of 3 to both sides? Still totally allowed. We still have the same initial step where I move that exponent out front, then I have parentheses 1 minus 9x times log base 3 of 3 equals x times log base 3 of 7. In particular, I know that log base 3 of 3 cancels to make 1, and I'm left with 1 minus 9x is equal to x times the natural log of 3 times log base 3 of 7. Then my goal is still to move all x's to one side, all terms without an x to the other, so I want to undo subtracting 9x by adding 9x to both sides. That cancels out to make 0. I'm left with 1 is equal to x times the log base 3 of 7 plus 9x. Both of these terms still have an x in it, so I can factor out an x. For the first term, x times log base 3 of 7 divided by x leaves me with log base 3 of 7. 9x divided by x leaves me with 9. And then I still have x times something gross, although I'd argue a little bit less gross than the thing we had before. So I can still divide by that thing. And that's log base 3 of 7 plus 9. So as my final answer, I have 1 over log base 3 of 7 plus 9 is equal to x. And you might be saying, hold up, those are not the same thing. They look totally different. But let's check. If I were to use the change of base formula and confirm, these should actually give you the same thing. So on one line, let's go ahead and put the natural log of 3 divided by the natural log of 7 plus 9 times the natural log of 3. It's about 0.092839 blah, 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 blah. And for the next one, let's put what we got there. So that's 1 divided by log base 3 of 7 plus 9. They are actually equivalent answers. And you would find they were equivalent answers if you basically converted log base 3 of 7 using the change of base formula to natural logs and did a little bit of manipulation. You could actually make these equal. But either was considered equally correct answer on an exam. If you're told that you have to write things in terms of natural logs, I would go ahead and solve in terms of natural logs or just be very comfortable with using change of base formula at the end. But if you're not told what log base to use, be nice to yourself and pick one of the log bases that's already present in the problem, because then at some point you're going to find that it cancels out, and that's just one fewer logs that you have to keep track of. We also could solve equations that have logarithms in them in the first place. So we're not only solving exponential equations, we could also solve log equations. And in particular, we can solve log equations by just using literally the definition of a log. And if we're going to do that, we need to get the log totally by itself first, and then employ the definition of log. You'll know that you want to use this strategy if you just see the word log appear once in the problem. So let's practice doing that. So the first thing we want to do is basically solve for the log here. So we're going to kind of treat natural log of x as though it's a variable. And if I'm treating that whole thing like it's a variable, what's the first thing I want to undo? I want to undo adding 3. So I'm going to subtract 3 on both sides. 3 minus 3 makes 0. I'm left with 2 natural log of x is equal to 4. And then as my next step, while I could be thinking, oh, I could employ the power rule and move the squared in here, you'll find yourself getting some extraneous solutions if you do that. So I actually don't recommend doing that. Instead, I would just divide both sides by 2, and you'll be left with the natural log of x is equal to 2. And now you're ready to employ the definition of a log. And to help keep me straight with the definition of a log, I may just rewrite that I know natural log as log base e. And now I'm ready to go to say that we have the same base to the output is equal to the input. So natural log of x is equal to 2 is same as e squared is equal to x, which is actually technically just a final answer. You also could plug this into a calculator to get its decimal approximation, but that's it. Now with logs, you do actually have to double check that your answer works with the domain at the end. So in particular here, what types of numbers am I allowed to plug into this log? X has to be strictly bigger than 0. And is e squared bigger than 0? It is. E squared is approximately 2.7 squared, and that's still a positive number. Go ahead and try this next one yourself, and don't forget to check your answer with the domain of a log at the end. Here we want to employ a similar strategy, so we're going to still try to get the log base 2 of 3x by itself first. So in particular, I'll have to undo adding 8 by subtracting 8 on both sides, and that leaves me with log base 2 of 3x is equal to 2. Now I'm ready to employ the definition of a log, so this means 2, same base, to the output 2 is equal to the input 3x. 2 squared is something I actually know, that's 4. And then as a final step, the last thing I would do to get x by itself is divide by 3 on both sides. So x is equal to 4/3. Then I want to double check with the domain of a log. So in particular, 3x has to be bigger than 0, which even after dividing by positive 3 on both sides means x has to be bigger than 0. So I'm okay because I got a positive 4/3. You also could use the one-to-one property of logs just like we use the one-to-one property of exponents, and that is to mean that if I have log of the same base of something equals log of the same base of something else, I can set those two somethings equal to each other. So that in particular is what I'm going to exploit in a problem like this. So if I have the natural log of x squared is equal to the natural log of 2x plus 3, then it better be true that x squared is equal to 2x plus 3. Now I just want to solve this using my normal methods to solve quadratics, which means here, since I have both an x squared and an x term, I want to move everything to the same side and set it equal to 0. I like keeping my x squareds positive just in case I'm going to end up factoring. So I'm going to subtract 2x and subtract 3. So then I have x squared minus 2x minus 3 is equal to 0. Then I want to ask myself what's going to multiply to negative 3 but add to negative 2. That would be negative 3 and positive 1. Now I want to exploit the zero product property, so our two many equations would be that x minus 3 is equal to 0, or x plus 1 is equal to 0. So adding 3 to both sides, that means x could be positive 3, or subtracting 1 from both sides, that means x could be negative 1. But don't just quite declare victory yet. We need to double check this works with the domain of a log. So it could be that x squared is bigger than 0, which even just kind of thinking about it, or x squared bigger than 0, negative times a negative is a positive. Positive times a positive is a positive. What's the only thing x can't equal? X can't be 0 itself. We're going to formally go over how to solve quadratic inequalities later, but for now it's okay if you just want to logic that out. But then 2x plus 3 greater than 0, that we formally know how to do. We would subtract 3 from both sides. 2x is greater than negative 3. And then we would divide by 2, so x would have to be bigger than negative 3/2. You also, alternatively, than finding like what the formal domain is, you could literally plug this number into the log to make sure what's inside the log is still positive. So for example, for 2x plus 3, you would plug in negative 1. 2 times negative 1 is negative 2, plus 3 is positive 1. That's still positive. You're okay. That's another way to double check the domain of a log. So either you double check both of these numbers are greater than negative 3/2 and they're not equal to 0, we're okay. And both of these numbers, if I literally plug them into the log, just show plugging in 3 for good measure. So 2 times 3 is 6 plus 3 is 9, and both of these, if you square them, 3 squared is 9, negative 1 squared is positive 1. Whichever log we plug into, we've always plugged positive numbers into the log and it fits with the general domain, so we're okay. Those are our final two answers. Go ahead and pause your video and try this next one yourself. So for this next one, I still have log equals log, so I can go ahead and say that means x squared is equal to 1. Then I want to undo that square with the square root property, so I'm going to square root both sides, and when I undo with the square root property, what else do I need to remember? The plus or minus on the square root. So x could be the positive square root of 1 or the negative square root of 1. And what is the square root of 1? That is just 1. So x is either equal to positive 1 or negative 1. And here, in particular, for x squared staying bigger than 0, remember that just means x can't be 0. Or you could just literally plug it in. So if I do 1 squared, that's 1. That's bigger than 0. Great. If I do negative 1 squared, that's also 1, which is bigger than 0. Great. So both of these solutions work. We may have to do a little bit more manipulation to make it look that way. So in this case, it looks like here I've got some numbers chilling outside the log, which I can either bring in Or I can also divide or multiply to get rid of them. In this case, we're going to do kind of a combination thereof. So here, since my goal is to solve for x, I think I personally don't want to really touch what's inside the log dealing with the x. So I'm going to get rid of this 1/2 out front first. How do I undo multiplying by a half? I want to divide by a half on both sides, which is the same thing as multiplying by 2. That cancels to make 1. And what I've written over here, keep in mind that 2 is really going to be multiplied again with numbers on the outside. I'm not touching anything inside a log just yet. And 2 times 3 gets us 6. Log base 4 or 5. Now I'm going to use the power rule and say that I know a 6 out front of the log is same as putting the 6 inside the log. And just from experience, I know utilizing the power rule whenever it's a constant like this is going to be generally a little bit nicer to make sure that you don't get solutions that are extraneous, meaning they work algebraically, but then you plug them in and they no longer work anymore. You're less prone to get that if you do that with constants like this. We could have also done that with the x over here. It's just sometimes that can lead to more extraneous solutions, which I personally don't want to deal with when I can avoid them. So that becomes log base 4 of 5 to the 6th equals log base 4 of x. And to me personally, 5 to the 6th is messy enough. I'm just going to write that as 5 to the 6th. Now we have log same base equals log same base. So x must be equal to 5 to the 6th, which if it was a test, I would say is completely fine to leave as is, because that is not a very nice number. Or you could plug it into a calculator to find out what it is. You should double check it works with the domain of the log. In particular, if I plugged in 5 to the 6th for x in this first log, what was inside the log would indeed stay bigger than 0, so you're okay. For this next one, this might at first look like a situation where you want to make it as log equals log, but you should be thinking something special happens if I have log base 4 of 4. What is that number? That is just 1. And what you want to be careful about is if you're going to use this notation where you like cross them out like this, you want to make sure you remember that's 1, because that's a place a lot of people messed up, is they cross it out and they just ignore that term entirely and treat it like it's 0. It's not 0, it's 1. So we have 2 log base 4 of x minus 2 plus 1 is equal to 2. And now I just have one copy of the log, so I'm going to actually just solve for that log again. So in particular, I'm going to undo adding 1 by subtracting 1 on both sides. That gets us 2 log base 4 of x minus 2 is equal to 1. Then I'm going to get rid of multiplying by 2 by dividing by 2 on both sides. And that gets us log base 4 of x minus 2 is equal to a half. Now I'm going to use the definition of a logarithm. So this means that this is 4 to the output is equal to the input. 4 to the 1/2 is the same thing as the square root of 4, which is 2. Being equal to x minus 2, and then as a last step I would add 2 to both sides. So 4 is equal to x. And then you want to double check that works with the domain of the log. In particular here, x minus 2 has to be bigger than 0, so x has to be bigger than 2, which it is. Or you could literally plug in 4 and double check that's bigger than 0, which it is. This is an example where I can't really avoid the fact that I've got a 1 and a bunch of logarithms floating around. So here I want to use my properties of logarithms to somehow condense this. And there's 2 different ways I could do that. I could either rewrite this as move all the logs to one side and then combine them and leave one side as a 1, or I could rewrite that 1 in terms of a log. I'm actually just going to move around my logs and then apply these rules, but keep in mind you might see some other solutions where they instead rewrite that 1 as log base 10 and then move accordingly. So here, if I'm going to move all my logs to one side, in particular I'm going to subtract log of x minus 9 from both sides. That cancels out to make 0. I have log of 8x plus 9 minus log of x minus 9 is equal to 1. And now I want to condense these to make one log so that I can then just exploit the definition of logs. And what does subtracting outside the log become? That becomes division inside the log. So this becomes my new equation. And now I can employ the definition of a logarithm. Keep in mind, if I see a log without a base written, that's secretly base 10. So this means I have same base 10 to the output 1 is equal to the input, which is this entire thing. And now my goal is to solve for x. Whenever I have an equation like this, I personally want to get rid of the fact that I've got x's in my denominator. And how do I undo division? Well, I just multiply. So I'm going to multiply both sides by x minus 9 in parentheses. That cancels out to make 1. X minus 9 times 10 is the same thing as 10 times x minus 9 equals 8x plus 9. Then I'll want to go ahead and distribute the 10. So that gives us 10x minus 90 is equal to 8x plus 9. Now again, my goal is to get x by itself. So I'm going to subtract 8x from both sides. That gets us 2x minus 90 is equal to 9. I'm just going to rewrite the problem up here because I'm running out of room. Next, I want to undo this subtraction by adding 90 to both sides. So 2x is equal to 99. Divide by 2 on both sides, so x is equal to 99 over 2, which is 49.5. I do want to double check that works with the domain of the log. So in particular, we need 8x plus 9 to be bigger than 0, and x minus 9 to be bigger than 0. This is a case where x is big enough that maybe I just want to find out the general domain of each of these logs. I subtract 9 from both sides. X has to be bigger than negative 9. Divide by 8, divide by 8. X has to be bigger than negative 9 over 8. And x has to be bigger than 9. Well, 49.5 is bigger than both of those, so we're okay. And you would find if you plugged it into either that the result would be bigger than 0 as well, so you are good. And here, just keep in mind that the correct way of doing this is to go ahead and, like, if there's an x squared in there, keep it inside the log. What you don't want to do is move an x squared that is currently inside the log outside the log, because then you're going to lose solutions. So do not do this. This loses solutions. Keep x squareds inside those logs. The last method that is sometimes helpful to solve exponential and logarithmic equations is U substitution. So what would that look like? So in particular, if you have an equation like this, well, with this middle term is such that that middle term squared gives you the first term, which in this case is true. That becomes 3x all squared is 3 to the 2x. Then you should be thinking I can use U substitution. In particular, I'm going to make u, that middle term, 3 to the x. That makes u squared, 3 to the x all squared, which is 3 to the 2x. So I can rewrite this problem in terms of u such that first term is u squared, that middle term is u, and all those other terms stay as is. So I have minus 6 plus 9 equals 0. So all I did was I rewrote 3 to the 2x is the same thing as 3x squared, and I'm calling 3 to the x u, so that's u squared, and 3 to the x is rewritten as u. Then I can solve this equation in terms of u. In particular, I may want to see if this factors. So is there anything that multiplies to positive 9 and adds to negative 6? There is. That would be negative 3, so this is u minus 3 times u minus 3 is equal to 0. Then I can solve this in terms of u. In particular, I would set up two mini equations of u minus 3 equals 0 and then another copy of u minus 3 equals 0. In this case, that happens to be silly because they're copies of each other. Last step, you would add 3 to both sides. And if I wanted to solve in terms of u, I would be done. But u actually meant something. It meant 3 to the x. So I actually want to go ahead and plug in that u is 3 to the x, and I've set that equal to 3. And 3 is the same thing as 3 to the what power? First power. So that means x has to be equal to 1. And that's exactly what this is saying in just more words. That if you notice this pattern, then you are a candidate for using U substitution. So here in particular is another case where that would be true. So go ahead and pause this video and see if you can do that u substitution yourself, and then let's compare with what we get here. So here my u would be e to the x, which means u squared is e to the x all squared, which is e to the 2x. So this is u squared minus 8u plus 15 is 0, replacing e to the x with u, e to the 2x with u squared. Then I want to ask myself, what's going to multiply to positive 15 and add to negative 8? That would be negative 5 and negative 3. Now I can set up my two mini equations. So then I have here u minus 5 is 0, u minus 3 is 0. So u is equal to 5, and u is equal to 3, adding 5, adding 5, adding 3, adding 3. Now I replace u with what it actually is, which is e to the x is 5, and e to the x is 3. And in this case, I can't cleanly rewrite these both in terms of powers of e, but I can undo that exponent with a natural log. And this in particular, picking natural log itself is going to be super nice, because if I natural log both sides, that x moves to the front, so then I have x times the natural log of e is equal to the natural log of 5. And what is the natural log of e? That is 1, so x is equal to the natural log of 5. And on this other one, you do the same thing. So x times the natural log of e is equal to the natural log of 3. Keep in mind I can only natural log because this guy is a positive. If that were a negative number, it doesn't work. I can only plug in positive numbers to logs. Natural log of e is still 1, so x is equal to the natural log of 3 is my other solution. As always, please take a look at your textbook. They have even more examples, and please let your professor know if you have any questions.